Assalamualaikum and hi to all students. Hope all of you are doing fine and great at home. Alright, so we meet again here in our recorded version of our lecture. So we will continue on this topic 10, which is on analysis of variance. So before we move further, actually on this topic, so what we want to know is actually what is this analysis of variance? Am I right? So the abbreviation is ANOVA and the full term is analysis of variance. Alright, so looking at here, basically in statistics, one way analysis of variance, or we abbreviated like just now and like I'm saying, ANOVA, is a technique that can be used to compare whether two samples means are significantly different or not. Okay, this is by using F distributions. So this is actually the full definitions lah on what is actually analysis of variance is all about. And so basically the main thing or the main point that we are looking at here is to, what is it just now? To determine whether there are any statistically significant differences. Okay, mind the difference, the terms there, statistically significant differences between the means of two or more independent unrelated groups. So independent again, unrelated, dependent is related, because dependent means each of it are depending on each other. Am I right? So but basically for ANOVA, it is to determine whether there are any statistically significant differences between the means of two or more independent or unrelated groups. Okay, basically although we tend to only see it used actually when there are actually minimum of two rather than two groups. Okay, means that many is much more better to see the difference, because if two, let's say, we can easily spot the differences. All right, so that's why minimum is actually two, but should be more because we are comparing. All right, so that is the basic terminology of analysis of variance or ANOVA. So this slide is showing the basic terms of analysis of variance. Okay, so the thing is, analysis of variance is to very widely used procedure. So basically looking at the basic definition that I have mentioned just now, it is actually a procedure which determines whether differences exist between population means. Okay, as written here lah. Okay, population means, differences exist or not between populations means. That is why I said that basically it is minimum between two or more populations, but because logically if you look at only two, it's like easily to spot. Am I right? So more than that, which makes it much more harder to spot the differences. So that's why minimum at least two, but much better is three or more populations. But the thing is, the main point that we are looking at here is we want to know whether is there any differences exist or not between the population means. Okay, so name is analysis of variance. So variance means that the vary or differences. So that's why the terminology is analysis of variance, even though we are looking at the population means. So of course, because we want to know whether there are variances, I mean the differences among this population means. So that's why the use of the name of analysis of variance here. Okay, so a procedure which works by analyzing sample variance. So that's why again here, this is just to recap lah, the definitions of this analysis of variance technique. Okay, so at this side, okay, so the one ANOVA is actually comparing the means between the groups that we are interested in, groups okay, interested in, and to determine whether any of those means are statistically significantly different from each other or not. Alright, so that is the way of ANOVA comparing the groups, and the purpose is again to see whether there are statistically significant differences between the means of this unrelated group. Unrelated, yeah. Okay. So if there is only one factor with two or more treatments, okay, one-way ANOVA is used to determine whether their population means could be equal. So basically when we're testing or proving this, so we would have this hypothesis null and also this hypothesis alternative involved. Alright, so because we want to see whether the population means different or not, am I right? So basically we'll put some sort of a hypothesis that is contra to this one, which is the hypothesis now saying that the populations means of all of these groups are equal. So this is what the statement means. All right, so and then of course the hypothesis alternative is the one that we are trying to test, which is the population means of these groups are different. Okay, so we'll be looking at that hypothesis testing later on. Okay, so one-way ANOVA also be applied to compare treatments that cannot be randomly assigned. For example, we compare starting salaries among graduates from various fields of studies. Of course, it cannot be randomly assigned because you know, each of these people or individual will get their own specific amount of salary, so cannot be randomly assigned. Okay, and then other assumptions of one-way ANOVA: the populations are normally distributed, the population variance are equal, yeah, and the samples are independent. So basically this is back to the definitions of this ANOVA. Alright, so again here we are talking about one-way analysis of variance or ANOVA. So again, independent samples, yeah, are drawn from K populations. So they have this few populations and we take samples. So let's say we are talking about, for example, in this slide showing we have three lah, for example 3 populations. So basically the K in this example is equals to 3. So that is the population. So for each of these population, as we know that each of it will contain its own mean and its own variance, of course. So basically mean of the population will be denoted as mu, and this is the variance sigma squared. Alright, and 1 is for the population 1, and then mean here is for the sample, which is x bar, and s1 s squared for population 1. Same goes to population 2, population k. That sorry, this is not 3 lah, but I just assume that this is 3, but it can goes up to k, meaning that it can be let's say your population you have 5, so your k it will be equals to 5 lah. So this is just a notation to the numbers of the population that is that we are looking at. Alright, so up to k populations. Alright, so these populations are referred to as we call as treatment. Then it is not a requirement that your N1 or your population 1 must be equals to population 2 or equals to population K, meaning that what is N? N is the sample size. What does this statement means? This statement means that it doesn't compulsory, or it's not a requirement that the sample size must be equal for all of the treatments. For example, let's say your sample size for population 1 is 6, but then your population 2 you have sample size of 3. Okay, so it can be, but it doesn't mean that if sample size of population 1 6, sample 2 must follow the same. Okay, so this is what the statement means here. Alright, so now looking at this one-way ANOVA, we go into this part, the one that I mentioned just now on defining the hypothesis itself. So again, the one that I mentioned to you just now is, this is the one that the objective, right, that we want to achieve by doing this ANOVA, which means that we want to see whether there are differences or not between the population's mean. Okay, so basically this will be coming the hypothesis alternative, which at least one means differ, means that one of that population means differ. Okay, so of course your hypothesis now would be the contrary, am I right, to your hypothesis alternative. So hypothesis null will become stating that all of the populations are equal to each other. So we are trying to test this hypothesis and to see whether it going to reject or not your hypothesis null. Okay, so basically the first steps is defining the hypothesis itself. Okay, so in this part, okay, it can be either your hypothesis now is always equals lah, and then the one that we are going to test is whether is there any differences or not between these population means, right? So it can be either at least one of these means are different. It also applies to the objective of this ANOVA, right? Or it can also mean that when you are saying that we want to test whether all the population means are same or not, I mean, is there any difference or not? It can be also at least one, or maybe all the population means are not the same. That's why not all mu j are the same. It can be also, but still it concludes to the same objective of ANOVA, which is it wants to see whether there are statistically significant differences between the means or not. So either one, or it can be also all of the means are not the same. Okay. Okay, so two types of variability. Variability, the variances, the differences. Okay, so this is variability. Okay, variability, the differences are employed when testing for the equality of the population means. Alright, so we are going to look at these two types of variability or differences when we testing for ANOVA. So this come into two definition that come into our calculations lah that comes into this ANOVA procedure, which is the first one, sum of squares treatment or SST expresses the amount of variation that is attributable to the treatments variation between treatment groups. Okay, which means that, like I said to you just now, the groups, right, or the population can be like three, means that two or more. Am I right? So we measure also the variation or differences between these groups. Okay, and the other one is the sum of squares error, SSE, which expresses the amount of variation due to sampling error. But this variation or differences is occur within treatment groups. What does it mean? Let's say you have group 1, group 2, let's say you have 3 lah. Okay, so what I'm talking about SSE here is the differences inside this group itself. But for this one, okay, they are talking about in between all of this, the difference. This is what is measured by the sum of squares treatment. Compared to sum of squares error, it only measure the variation that is happening inside the treatment group itself. Let's say treatment group 1, so inside it they want to know the differences that occur inside this. Okay, so this is what the difference of sum of squares treatment and also sum of squares error. So this is a type of variability that we are measuring. Okay, when we want to test the equality, the population means 1 equals to population 2, right, of the population means. So again, this is what being measured in this ANOVA. Okay. Okay, so SST is the sum of squares differences between individual treatment means the average and also the grand mean. Oh, okay, so what is the grand mean? Now they mention into the grand mean. Okay, so basically when we have, like, say we have this one population or samples lah. Okay, so we have, let's say we have sample 1, so we have the data lah for all the sample 1, for example. So when we measure the mean, we're going to add up, right, everything inside, I mean every observation inside that sample. Am I right? So let's say lah, let's say you have group 1, maybe just I put a simple one lah, maybe the data for this group 1, maybe you have 2, 3 and 4, for example. So the mean of this group 1 is you plus everything, am I right? You plus everything and divided by what? By the number of these samples lah, which is 610 divided by 3. Not a good example. Maybe I take simple one lah, perhaps this is much better, so easy. I mean, just straight away, for example, we have 2, 3, 3. Still not nice. 6, 4, it should be here, sorry. Maybe I just edit this. Okay, sorry. Okay, I draw another example. Maybe I have 4, 3, 3. 4, 3, 3 is 10 divided by 3. This one, this is a simple one. I take 3 lah, easy. Alright, for example, I have this and then I divided by sorry, not divided by 3 yet. This is this, for example, this is the sample of group 1, for example. So 3 3 3. So how do I get for this mean for this group? I add up everything, am I right? 3 plus 3 plus 3, so you get 9 divided by the sample size, which is 3, so you get 3. Like I said to you, just want to use a simple one lah, data for simplicity, but it's okay. Like for just now, let's say 3 plus 3 plus 4, you get 10 divided by 3, so you get in decimal places. It's okay. Okay, this is for simplicity of me explaining to you. So when we talk about this mean is individual for each of this group. But what is it, this grand mean? Grand mean means that when you have let's say you have 3 groups lah, for example, you have group 1, group 2, group 3 that you are looking at, and you have few samples here. Like I said, here is 3 3 3, maybe here it can be 2 6 2, 1 3 2. So this one basically you have its own mean, am I right? So mean for this group 1, and then for this group 2 you have mean for group 2. Okay, and for group 3 you have mean for group 3, am I right? So this is individual means. So grand means grand mean meaning that you take all of these observations. Okay, for example, let's say you have counted for the mean for group 1, mean for group 2, and mean for group 3. So you take all of this and you divide it by all these 3, so you get the grand mean for all of these 3 groups. This is just for example only. Okay, so that is grand mean. So you take the whole and you divide it by 3. Like for example, this one you get 3. Maybe here, maybe for example, maybe here you get what, 4 and 10, so 10 over 3. Here you get 5 6 6 over 3, so you get 2. So you add up this one and divide it by 3, you get the grand mean. Means that the grand mean is the mean for the sample means. Grand mean is actually mean for sample means. Okay, so if you look here at this formula given for grand mean, also is this the same meaning also. That is the way of me explaining to you. Grand mean here is basically the mean of the sample means. That's the definition. Alright, so looking at this notation, this is to denote that you are calculating for grand mean, not mean. If mean, you put it or not, use notation of x bar, am I right? So this is x double bar, because this is grand mean is equals to mean of the sample means. That's why you can see here either you use this formula or the second one. So looking at the first formula, okay, they take all the sample sizes 1 divided by n and times with the number of treatment. Means that for example you have 3 groups now, so up to 3, and this is the sample size for that particular group. Okay, and you take all the observation inside that particular group 1. Okay, and you add up until group 3. Same goes to here, either you can use the other formula. So you take 1 divided by the sample sizes, and you take this k, which is, this is the total of the group treatment, and you times the sample sizes of group of, let's say this is, you are talking about group 1, so sample size for group 1 times with the mean for group 1, so you times in. So basically, okay, it is just the same. What I'm trying to tell is that grand mean, you go and take every group means and you just find another mean for the whole sample means. So this is what it means here. Alright, maybe we can look at examples of calculating this later on. Alright, so whatever it is, now looking at this notation down here, nj is the number of observations of the j treatment. So let's say treatment, yeah, let's say you have group 1, group 2, and group 3, for example. So this is sample size for each of these. Okay, x bar j is the mean of the j treatment. So like I said to you just now, x bar for 1 means that you are getting x bar or the mean for the group 1. X bar 2 means that you are searching for the mean of the group 2, and x bar 3 means that you are talking about the mean for group 3. Alright, so this is what this notation means. And then Xij is the I's observation of the J treatment. So I observation of the J treatments, meaning that in that particular group, so which is the observation. For example, like just now I give to you group 1, you have for example, you have 4, sorry, you have 3, 3 and 3. So Xij means that the position is number 1 in this group 1, number 2 in group 1, number 3 in group 1. So this is Xij meaning. Okay, K is the one that I mentioned from just now, the number of treatments. So the how many treatment here? We have 3. The example that I'm sharing, that I'm using here. Okay, and then N is total observations. How many is the observations here? This is N. So N is containing the total observations. Let's say your sample size of group 1 is 3. Maybe for sample size of group 2 is 2, and maybe here you got 3. So you add up and you get your grand total for this. And for whole observation. Okay, so but let's see if your N is equal for each of the treatments, so you just add up everything lah. It can be same, it cannot, it can also be not same, the N. Alright, now just now is the first variation that we are measuring. The second one is SSE, the sum of squares that measure the differences between observed value and the means of their respective treatment groups. So this is within the treatment groups. All right, so SSE here, we can see that the formula here is K is the treatment group and NJ is for the sample size of that particular group. Let's say group 1, so you're talking about that sample, not the N. Yeah, so let's say this one you have 3 groups, so of course here is 3 lah, will becoming 3. This will become 3 and you start with 1, and then you take the summation of NJ. What is NJ? NJ is your sample size of that group that you are measuring, so goes to this one. Alright, and you minus with the X bar of your group that you are measuring squared, or it can be you use this formula, either one. Okay, maybe we can look later how we're going to apply this SSE formula. So basically S square is actually variance, but variance of the treatment lah, which means that variance of that particular each group of the particular each group. Okay, so we are going to need to count for the SST just now here, SST, and we also need to count for SSE. Okay, once we get both of these, then we go into the third part, okay, which is on the test statistic. Like I mentioned just now, this ANOVA is measured by using F distribution. Okay, so we need to look at F table. Later on we'll see on this F table. So, and also like we have done previously, the same thing, when we use this F table, of course we need to have one part which we calculated. So this is the part which we calculated, which is this test statistic. So the formula here is MST divided by MSE. So what is this MST? So MST is the one that we take from SST. So here you already just now you already get the SST value, isn't it? So we need to count for the MST. So MST is actually equals to the value of the SST you get just now divided by K minus 1. Remember again, what is K? K is the group. Okay, and here MSE, how do you get MSE? You take the value of SSE divided by N minus K. So what is N minus K? So N is actually the sample observation, right? The one that you get. Let's say you get the whole observation, you get 16. So 16 minus with the treatment group, how many group there? So this is MST and MSE. So you divide both of these, MST and MSE, you will get the calculated version of this F statistic, which you need to compare with the one that you get from the table. Okay, so basically MST is the mean square treatment and this MSE is the mean square error. Okay, suddenly my font become big. Alright, okay, so now we look into this one. Maybe some of you are a bit like not very comfort yet, right? Because I just expose you to all of this terminology. Okay, so we need to try it on so that we can get used to how to calculate, especially on the SST and SSE. What does it mean, how to apply into that formula? Okay, later we'll see one example to expose you to applying the formula there. Alright, so this ANOVA table, so this is the ANOVA table. Okay, and how do we get it? This is the source of variation, treatment, error. The one that I mentioned to you just now, there is a two type of measurement of variation or variability that is involved, which is treatments and error. So sum of squares we get from this treatment and also SST. Remember just now the formula how we calculate. Later on we'll see how we want to calculate for this one. And for each of these, they have their own degree of freedom, which is for this treatment, they have degree of freedom, which is k minus 1. What is k? K is your group, the number of population there. Okay, so this is the DF. Mean square is here. Okay, the mean for the mean square of these sources of SST, so MST. Now from the sources of variation from the error, which is SSE, and this is degree of freedom, and you get MSE. So this is the total of the sum of squares, I mean everything, SS, which is this total lah. Okay, and the degree of freedom here is n minus 1. Now sum of squares total is equals to these two, SST plus SSE. Here both of these lah, total of the sum of squares or the variation. So now we want to know the decision rule. How you want to know? You reject if your calculated one is more than the one that you get from table. Okay, F table. So that's why I said to you, it's just the same. Like previously, I've explained that whenever you get the value, you have this some sort of decision rule, right? From the calculated one and from the table. Same goes to here. So basically, this one is from the calculated one. Calculated statistic. Alright, and this one is from the table. Alright, same also. The way of we may compare, and whether we want to decide on the decision rule is just the same. Okay, so now we look into the characteristic of the F distribution. This is the table that we are looking at. So we want to know on what is this F distribution. Like the one that I have exposed to you previously is what? The T table, the standard normal table, am I right? So that standard normal table, we have this shape of what? Still recall the bell shape, right? This is for normal, normal. Okay, normal table. This Z table lah. Alright, so this is on F distribution. How does the table look like? Alright, so for this F distribution, it is a continuous and positively skewed distribution. So when we talk about skewed, so in Malay we call it as terpincang, right? And it values range from 0 to infinity, of course, because it's positively. And as you can see here, this is the illustration of this F distribution. Alright, and like I said to you, it is skewed, so skewed to the right because it is positively. It's mentioned that it is positively skewed, so of course going to the right, and you see here it's going to infinity here. So starting from 0 to infinity because it is positively skewed. So there is a family of F distribution, and each member of the family is determined by the numerator degree. So we have both. We need to use 2 of degree of freedom. So numerator degree of freedom, which is V1, and the other one is denominator degree of freedom, which is V2. And as you can see here, from this value of F, because each of the T, for example, and Z also, we have the value that we need to read from the table. Am I right? So for F, the one that you need to have in mind for you to read the table is you need to have the value of alpha. What is V1? V1 is a degree of freedom for the numerator. Okay, and V2 is denominator. So numerator and denominator is the one that you get from this formula here. Okay, we go back to this slide. Alright, so this is your MST and MSE, numerator and denominator. So each of it, SST and MST and MSE, they have their own degree of freedom, right? For SST, they have K minus 1, SSE, they have N minus K. So that is your degree of freedom of numerator and this denominator. Okay, so degree of freedom for numerator is K minus 1 and denominator is N minus K. Alright, so after we have all that value, then we just read from the table of this F table. Okay, so that's all. This, the one that I explained from you from the beginning just now, which is we are talking about this defining the hypothesis, and then we have this calculating of what is the variation that we are taking into consideration or we are measuring here, which is SST and SSE, and also all this calculation from the test statistic, the one that you need to calculate, and then the degree of freedom for numerator and denominator for you to read from the F table. Alright, so done with that, we have know the step by step the procedure. Now we go into the one example here for us to get a better understanding on how actually we want to apply this. Okay, alright, so looking at here, a major computer manufacturer has received numerous complaints concerning the short life of its disk drive. Okay, most need repair within 2 years. Since the cost of repair often exceeds the cost of a new disk drive, the manufacturer is concerned. In his search for a better disk drive, he finds 3 new products. He decides to test 3 plus his current disk to determine if the differences in lifetime exist among the product, which means that he have the new one of 3 new product, and he wants to compare with the one that he's using right now, which is the current disk drive. So actually he's comparing between 4 population or groups here. So he takes a random sample of 5 disk drive, which means that for all group he takes same n, which is 5, and links it with the computer. So the number of weeks until the drive breaks down is recorded and it's shown below. So for this for this example, okay, the n is similar because he takes 5. Okay, 5 here for each of these treatment, that 1, that 2, that 3, that 4. All right, so now you have this treatment, and how is your that's your treatment lah. So n, that your treatment here is K equals to 4. Your n is basically, this is 5, right? You have to add up 5 plus 5 plus 5 plus 5, so your n is basically 20. So this is what you can list out first. Alright, now they give us, do this data allow us to infer at 5% significant level? So now you have your alpha as well here. Okay, 0.05. Alright, so basically we go back to the root of this question. The objective is to see whether there are differences or not of the lifetime, right, of the disk drive. So basically it goes to ANOVA, and you know that the population here or the group here is more than 2, of course, obviously, right? So now we started with the first step, which is on the hypothesis testing here. So basically again, ANOVA will put hypothesis, the hypothesis now here is all the populations are equal lah. So in this case we have 4 groups or populations, which is mu1 up, we make it we define the statement of the hypothesis now of the mean population of group 1 equals to group 2, group 3, and group 4. Now, of course, in the contrary of this hypothesis now is the hypothesis alternative, which is at least 2 means differ. So like I said to you just now, as long as it wants to see or measure there is any differences between the mean, no matter they're saying only 1 or 2 or all the population are not different, are not same. So basically it's still refer back to ANOVA lah, because we want to see the differences, alright, among the population means. Okay, but for this question, at least 2 means differ, at least 2. Alright, so the sample means and variances are summarized as follows. Okay, so we have this data lah calculated for all of these groups. So how do they get this one? How do they get this x bar? Okay, again, actually this they provided to us already the data. So we have this type 1 78 plus, we have the observation for type 1. We have 78, 92, 101, 105, 98. Am I right? So how do you get this x bar here, class? Okay, this x bar is actually the mean for this group 1. So how do I get this? How do we get this? So we add up we take 78 plus 92 plus 101 plus 105 plus 98. And then you divide it by what? Divided by 5. You should be getting 94.8. Okay, so this is how they get the sample, the group mean for this group 1. Same goes to group 2. So you take all the data and you divide it by 5. Here also the same. So now you already get for all of the group, right? So the one that I mentioned to you just now, what is the grand mean? The grand mean is that you take all the sample, the group mean, 94.8, 113.4, 126, 107.6, right? So you divide it by all these 3 groups, which is 4. So you get the sample, you get the mean of the sample mean, which is the grand mean. So basically this is what I'm saying to you just now. You find for this mean, you find for this mean, you find for this mean and this mean. Am I right? So you take all of the mean here and you divide it by all the group involved. So that is what the grand mean is all about. Okay, the grand mean is the mean of the sample mean. Okay, so settle here. Alright, now we go into the SST here, sum of squared treatment. So what is the formula for this sum of squared treatment? So you go again here, SST. What is SST? Okay, so SST, you take here the n, which is the total of your this is not total, this is the group sample size. Okay, and you take the mean and you take the grand mean, you square. Alright, so basically you take here for the sample 1. Of course lah, each of these is the same. Actually 5, everything also same, right? The sample size for each. And now for the group 1, what is sample mean? 94.8. You minus with the grand mean squared. Now sample mean group 2, you minus with the grand mean. This one you take the x bar 3 and you minus with the grand mean double bar. Now you take the sample size for group 1, 2, 3, 4. Okay, minus with the grand mean squared. So you should be getting your SST. Alright, so this is how you calculate for SST. Now you go to SSE. So how is SSE? SSE, you take the so here for SSE, we take the formula here. From the, how do they calculate here? SSE, now they take the number of your group here, which is 4, times with the here is 1. Okay, so this is the variance. So they times with the variance for each of it. Okay, so here they have this variance for the group 1. Okay, variance for group 2, variance for group 3, and variance for group 4, and the times with the group. How many group? This is SSE. Okay, if you can see here, the variances for the group, for each group. So how do they get the variances? How do we calculate for variances, class? Still remember? So we use the formula. So basically they have already initially calculate for the variance for each group, so make it easy later on to calculate for this one. So basically it's the same like if you use here also. Okay, you need to calculate for the you take this is SSE calculation. How do they calculate this? They take the x minus, the sample observation minus with the variances of that particular group. So basically it goes back to the root, which is you calculate the same as you calculate for the variances for this, like say for group 1. So you take for group 1 and you calculate. Okay, so it's just the same here. So let's say if you're using this one, so you need to calculate one by one. So now they just straight away take the how many group here, and they just times in with the variances. Alright, for all of that group. So here they have these variances for group 1, group 2, and group 3 and group 4. They just substitute inside and they get this SSE. So sum of squares total is the whole variances that we are measuring here, we take both lah, we just add up. Alright, but it does not stop here. We need to go into this ANOVA table. How? We have these treatments for SST and this SSE. Am I right? The one that we get just now. And what is the degree of freedom here? This is K minus 1. Right, 4 minus 1, and this is n minus k. How many n here? 20. How many k? 4. So you get 16. So numerator and denominator still remember? Alright, so how do they get this? That statistic. MST divided by, sorry, here we go back to this slide here. How do they get this F statistic? We take MST divided by MSE. How do you get this in advance? You need to divide by your degree of freedom first, okay, and then only you can plug in into this as the formula of your MSE. So for this one, okay, how do they get this MSE for this? Here they take 2517. Okay, 2517.75 divided by this k minus 1, which is 3. So you get this. Alright, same goes to here. How do they get 213.95? They take this 3423.20 divided by the n minus k, which is in this contact is 3423.20 divided by 16. So you should be getting the same answer here. And then you calculate for this one, which is MST divided by MSE, which is what, class? We take this 839.25 divided by 213.95 here. So you should be getting this one. So this is from the calculated F statistic, okay. And then from this is from the calculated. So how you take from the critical value? Critical value is the one that we always read from the table. So in this context, we need to read from the F table. So this is your alpha, the one that we have right from just now, 5%, right? And this is your numerator or denominator, the 3 one. Look back here, we get it from your SST lah, okay, which is your numerator and also denominator, okay. So numerator is the one that you get here from this one, yeah, MST. So you get 3 lah, because this is the degree of freedom. And this one you get from denominator, which is n minus k. You get from your MSE here. So you get n minus k, you get 16. Fine, then you read from the table. So the thing right here that I want to explain to you is how you get this 3.24. Now we look into this table here in this slide. So look at here, we have this V1 and V2, numerator and denominator. What is your numerator? Your numerator just now is 3, am I right? And then denominator, we go down here to 16. Okay, and what do you get here? This is the value that we need to read, which is 3.24. 3.24, okay. The one that we get from table. So then decision rule. So reject or do not reject? Reject. Why? Because your F statistic from the calculator is more than 3.24. The one that you calculate is 3.923, and obviously it is more than 3.24. So your decision is to reject H now. What does it mean? There is evidence to infer that the mean lifetime is differ between the 4 disk drive, because your H now is stating that all the population means are same, right? So when you reject, means that the mean lifetime between the 4 disk drive are different. Alright, so this is how we perform this ANOVA testing. A very simple example lah, to look and to boost up your understanding of this concept of measuring ANOVA. Okay, so this is another one that we can see on one-way ANOVA test as well. Alright, so here we have different club lah. Okay, we have club 1, club 2 and club 3, and all this data, and again the sample size for each of this group, yeah. So now I'm highlighting each of these group are same lah, because I have 5 here. Okay, so randomly select 5 measurement from trials, and at Okay, so now they also give you the significant level. So they want to see is there any difference in mean distance. So basically the concept still applies to ANOVA here. Alright. So one way ANOVA example here. So basically they have these three clubs, and as usual, we calculate for the X bar, which means that we total up this one. We get X bar 1. Okay, we add up, and we divided by 5. So you should be getting 249.2, and here also you get your X bar 2, and here you get your X bar 3. So basically this is the one that we calculated. And what is grand mean again? So grand means how do they get this? They take 249.2, so X double bar 249.2 plus weight 226 plus weight 205. Alright, divided by how much? By 3, because you have 3 right here. So divided by 3, so you should be getting 227 for your X double bar, or your grand mean, not green. Okay, so that's with the grand mean. Now we move to the next part, which is now what else do we have? Okay, for this one, not to get you confused, C is here, they are talking about the K lah, which is the group. Now because they are using club, so they say C, but basically they are talking about this K. So same, yeah, not to get you confused, K is equals to C, which is again this group K or C, which have 3, or we have this treatment lah. Okay, so and again X bar is the mean for each of the treatment. So and the sample size here for each of these club 1 is 5, so similar for each of these, right? So the total N here, how do we get N here? N is the total observation, meaning that N here is equals to N1 plus N2 plus N3, which is actually equals to 5 plus 5 plus 5. So you should be getting 15. Alright, so this is how we calculate this. Now we go to SST. How do we calculate for SST? Okay, you take the X bar, which is 249.2 here, you minus with your grand mean and squared, and you times with what? The sample size here. So this is similar like just now. Alright, and here for SSE, okay, so a bit different from just now, but basically it's just a similar calculation here. You take this each of this observation 254 minus with what? Minus with the sample mean of this treatment 1, club 1, 249.2 squared plus with this 263 minus with the 249.2 and up to 251, so you minus with 249.2. So basically maybe you're asking me why is it different. So basically is this the same? Okay, because here they do not calculate for the variances for this club 1. Okay, they did not calculate, so that's why they manually calculate all of this observation minus with its how to say, its mean here. Okay, for each of this item in the group, and then they start up with here also 234 minus with 226 up to 216 minus 226, then they continue 200 minus 205.8 up to 204 minus 205.8 here. So they need to calculate manually. So it's just the same. Okay, it's not any different. Either you can use this way or you can use this one. Which one? Here, inside here. So the difference here, yeah, just to emphasize, is that they already calculated in advance for the standard deviation for each of the group. So let's say you want to make your calculation much more easier, so you can use this option 1. Okay, you calculate first your variances here and make your calculation easier later, so you just times with the group. Or you can use also this way, option 2, but basically it's just the same like you use for the formula given to you. Alright, which is this slide, this one, yeah. So it's kind of just the same thing also. It's just the same. Why am I saying this? Okay, so you can look here that either you use your x for each of the group time minus with the mean, or you can take your total of your observations and you times with your what is it here, your variances. Okay, so let's say your nj, nj, for example here, nj for this question one here, because they calculated for the variances already, right? So how many is the observations for each of these? Nj for this one, n1, right? How much? 5, am I right? So 5 minus 1, you get 4. So for this one, 4, right? So you use 4 here. Okay, so for example here, let's say for example, perhaps we have 6 lah here. Your n here, n2 equals to 6. So basically it will become 6 minus 1, 5. So 5. This is for example, but for this discussion here, as you can see, your n is similar, right? So if similar, then we just put everything same lah. Like, but what I said to you just now, it can be also your sample n for each of the group or treatment are not same, am I right? So if not same, so you need to calculate each of it. But for this discussion, all of n are equals to 5. But just to highlight, let's say your type 2 is you have 6 data here. This is 5, this is 6, right? So of course for this type 1, you get your n 4, but this one is 5. So let's say for type 2, you get 5. For example, you get 5. So what you need to adjust here, you need to put 5 lah. If let's say the observation is 6, because you need to minus, okay? And then you times with your standard deviation. So this is actually the option here lah. Okay, if you get confused, why is it different, this example 1 and 2? It's not any different, just to show this one lah. Okay, so that option, example 1, they are using this formula. Okay, so they take this nj, nj meaning that the total number of observations in that particular group or treatment, and you minus 1, and then you times with the group standard deviation. And but for this one, okay, you need to take for the data for each observation, and you minus with your sample mean for that particular observations, and you square, and you just add up everything. So this example shows both calculations lah for SSE. Either use this formula here, or you can use this formula here. Alright, so now we look at this here. Once they calculated already, okay, for the SSE, okay, now they get this value here. Now you need to get your MST and MSE. So here you get 4716.4 divided by how many here? K minus 1, and this is n minus k, right? Your k is 3, so n is 15 lah. 5 times with 3, right? So you get this MST MSE. What do you get next is your F statistical value that you calculate. So you get this value. What is the next step? You need to read from the table. So you know the alpha is 0.05, right? 0.05. What is your numerator? Numerator is 2 and denominator is 12. Okay, how do I know this? We take from this one lah. This is numerator is for MST, right? So this is the one. K you use k minus 1, and denominator you get 15 minus 3, so you get 12. Okay, denominator is down, numerator is the one at the top. Okay, so you get your numerator 2, denominator 12, alpha 0.05, and you have this hypothesis, and you know that this is how the F table looks like, right? So you know that the critical value is the one that will become your benchmark here lah. Okay, so we straight away look at the table. If let's say your V1 is 2 and your V2 is 12, and here again, to highlight, this table is for 0.05 alpha. Okay, so we get the value of the f here is 3.89. Okay, so you get the value here 3.89, and then it become your critical value. Now you compare it with what that you calculate, which is 25.25. Obviously this is much more than your critical value, so we need to reject because it is in the rejection area. So there is evidence that at least one differs from the rest of the population means. So just now I forgot to highlight that the F table, yeah. Okay, this F table here is, when you read this, of course this one you read from numerator and denominator, and of course you also need to have this alpha. So this table is basically only for alpha 0.05. So if you have different alpha, then we need to read from different page of this alpha lah. Alright, so now that is for the second example, which I think should be ample enough, okay, for this lecture, in order for you to understand of calculating this step by step as MST MSE. Alright, so I hope that this lecture will help you out on the understanding of calculating for and testing for ANOVA. Alright, so that's all for our lecture today on this analysis of variance. Okay, so I hope that this lecture will help you out and go through again on the way of calculating it step by step. Alright, and thank you so much.